Hi everybody, I'm Stéphane Roche from the Catalan Institute of Nanoscience and Technology, and I have the great pleasure to give this pre-record talk for Materials for Humanity conference organized by our Singaporean friends. So during this talk, what I would like to show is our efforts and our in-house methodologies in order to investigate electrical and thermal property of highly complex disordered materials. And I would show that how we make use of machine learning as well as multiscale computational approaches, especially emphasizing our development of linear scaling quantum transport methods that can really allow to investigate highly complex forms of materials. So I will have three parts in the talk. First, I want to motivate a bit the type of material we are interested in and the methodology we are developing. And then I will illustrate more extensively on three different classes of materials. On one side, I will cover the composite, including reduced graphene oxide materials, and also polycrystalline graphene. And the last example I wanted to discuss is related to amorphous two-dimensional material. So we are interested in properties of very complex materials that are of interest for a wealth of application in energy, composite, biosensors, solars, and so on and so forth. In particular, we have interest in understanding the properties in graphene polymer composite. And that represents a great challenge because of the multiple types of disorder occurring at different scales. And here in these pictures, we illustrate the level of complexity, because disorder is not just embedded into a local atomic structure, but it's also present at different scale, where, for instance, you have here this kind of different flakes that are interacting, and then they are also hybridized with other kind of molecules and polymer. So that makes the situation extremely challenging from a computational point of view. But these are very important for companies because even if today we have a lot of those materials already embedded into commercial products, the way to further optimize their property is very complicated. And many companies need guidance in order to further improve the performances of their product. And this is a case I'm showing in this slide of the Spanish company Avanzare, which has some requirements in terms of thermal property or mechanical stability of the composite they are fabricated, and we are trying to help them to improve their materials. Another class of material which is very interesting for us is related to the so-called CVD grown catalytic vapor deposition materials, such as graphene as a first example, as well as a class of a lot of different materials. And they present the particularity that even though they are atomic monolayer, they have this very complex polycrystalline morphology. So they embed a lot of defects, which are this grain boundary and an additional numbers of disorder, which has to be investigated. And it turns out that this type of polycrystalline graphene is extremely important for all what we can consider high-tech application. And here, a big consortium, the Graphene Flagship, many partners are using CVD grown polycrystalline graphene for many type of application, from optoelectronic devices to flexible and optical sensor, medical implant, and so on and so forth. So there is a lot of interest to really optimize this device performances based on the understanding and the modeling of the materials. So predictive modeling is something that we are developing in my group. What does that mean? I mean, we want to really take into account the complexity of chemistry. And for instance, this is an illustration where you have this type of defect that are very damaging for graphene. So we need to have a level of high accuracy to capture those effects, and this requires to investigate the structure or the relaxed, the stable forms, and things like that. So since we are concerned by disorder material, quickly we are dealing with models which can have millions or even billions of atoms if we want to reach a scale which can be compared with experiments or industrial scale. So, of course, everybody knows that first principle calculation is the approach of choice for achieving such an accuracy in terms of electronic properties. But this is has limited scope. And if we want to investigate electronic or thermal transport, we need to, in disorder forms of those materials, we need to really find a strategy which is really like the multiscale approach. That is, you capture the most essential part of the Hamiltonian from a comparison between, let's say, a type banding model, and you compare bound structure with the first principle for small unit cell, and then you investigate larger and larger unit cell, and you also investigate the effect of single defects, and find a way to extrapolate on the type banding model. So this is very interesting, but it's not enough if you are interested or you're concerned by quantum transport. So given the size of the system, you really need to implement approaches that are, of a computational cost that is at most linear with the number of atoms, and this is the methods we have been developing. So then, of course, there are new type of simulation tools such as machine learning that can be very helpful in many regards. But let me first illustrate the fact that there is a need for multiscale approach for understanding the real property of the material. And this is a typical example of a simulation which lead to a float prediction in the sense that these people investigate sp2 amorphous or disorder graphene, and by increasing the degree of the number of defects in their supercell, they conclude, they found that the density of state at low energy was increasing. So they extrapolate that the conductivity would also increase with a degree of disorder by just also looking at the so-called participation ratio of the states, so the extension of the state. Well, it turns out that this result is misleading because at the end of the day, these materials, if you move in scale, you will eventually find that the system is an insulator and certainly not a good conductor. So we have been developing for several decades these so-called linear scaling quantum transport approaches that you can find all the details in a very recent review article published in Physics Reports, and those methods are capable of dealing with charge, thermal or spin transport. They can also include the effect of temperature and electron phonon coupling. You can also describe polar ionic transport and a lot of other things. So we have recently set up a web platform in order to connect with the larger community, to engage more researchers and students to the type of methodology we are developing. And so I invite you to look at this website, and if you're interested to collaborate with us, to register. the website. So with this type of methods, we can investigate structure that are really disordered and really complex and very large size. These are example of the typical models that we investigated, like disordered graphene using a molecular dynamic, let's say, synthesis, and or a purely topological disorder materials by changing the density of non-hexagonal ring. When we use these methods, we conclude not that the system is a metals, contrary to the previous paper I've mentioned. Although the density of state is increasing, these states that are created by defects are not promoting the mobility. On the contrary, mobility remains quite short, because there is a lot of scattering that occur at these energies, and eventually at low temperature, the system will become an Anderson insulator. It's also important, I would like to point out the use of machine learning. This is particularly important because we are interested in extremely complicated and disordered materials. So here we are showing an example of amorphous boron nitride films that are grown by MD. And the point is that in order to capture the proper structure, we need to get the realistic atomic interaction potential. And for doing that, we have developed a machine learning based approach, which can use a training set based on thousands of DFT calculation to extract force and energy, and so to extrapolate what will be the interaction between atoms depending on their local environment. So these are typical sample that we generate with this machine learning based potential with different resulting density of the structure. And we have also started to investigate the dielectric function of this material. I will comment on this later on in the talk. So let me go to this reduced graphene oxide based composite and polycrystalline graphene. So first of all, the people who are interested in composites based on graphene, they usually started with a graphene oxide, which is a highly disordered material because it results from a chemical exfoliation of graphite with the use of a lot of acid. And then at the end of the chemical treatment, you have a very large density of those defects, typically 60% of sp3 defect on this sp2 carbon membrane. So then you have a lot of different type of reduction approach to eventually eliminate a certain density of this oxygen atom that are stitched to the material. But you always end up with a system that will increase its number of non-hexagonal rings, this pentagon, heptagon, octagon. So the system becomes more and more amorphous, and these defects will have an important impact on the electrical property in particular. So as I said before, if you look at the resistance versus temperature, these were some measurements made several years ago. The system become very insulating at low temperature due to the presence of this type of defects, which in graphene introduce so-called intervalley scattering. Very recently, some colleagues from Italy have explored the impact of interflake interaction, which is one question that was opened by the industries. How can we find an optimization based on the size of the flakes, on the degree of disorder, and if the interaction between flakes is something that is beneficial or not to the final property of the composite. So this is a very interesting experimental study that has been made. What I would like to point out is this final conclusion that by looking at the temperature dependence of the resistivity, they can extract an effective localization length of the system, and they can look at all these localization length change with the degree of oxidation, the typical sheet size, or the thickness of the films. And one very interesting thing is the fact that this localization is delocalization increase by increasing the number of layers. And this is something we wanted to investigate it from the simulation side. So with a consortium, we have implement a multiscale approach in order to combine the EFT with step banding, with mesoscopic transport, and then to try to connect and to understand the experimental feature. And basically, we could find something very interesting and in agreement with the experiment, which is the following. By looking at the bulk transport of a multi-layer reduced graphene oxide with still a number of oxygen defects and structural defects, we found that typically the effect of the interlayer is damaging to the transport. So if you increase the number of layers, typically your mean free path will be reduced. On the contrary, when we integrate this type of structure and we contact them in a way which is similar to the experimental situation, then we find a kind of opposite trend, in the sense that by adding layers, the conductance that is measured between contact will increase with the number of layers for exactly the same number of defect and same defect density. So this is something which is a bit counterintuitive, but it is really related to the fact that the contact geometry in a composite, where you have flakes that are not all connected to the source and drain, brings an additional complexity which can be unveiled through the simulation. So as I said, another material of interest is this polycrystalline graphene, which you can grow at a wafer scale. So this is a mention to a very large European graphene flagship project, where we are working on bringing this two-dimensional material to a lot of application, and this type of large-scale material is a material of choice for high-tech application. So there are a lot of issues, because you have to grow these materials, and by at high temperature, usually on a metallic substrate, then you have to transfer this material to an insulating substrate. So there are quite a number of defects that are present and needs to be accounted, and the damaging impact of different level of different type of defects is important to quantify. So it was shown by this group of Zhangfang Liu in China that because everyone tried to accelerate or to optimize the growth towards single crystal, but so there are plenty of possible alternatives to increase the growth rate. And this is actually very important, the key question for industrial graphene production, because we need to have a growth at sufficiently low temperature in order to have a minimal energy consumption. Otherwise, the system will be quite poorly performing for application. So there are plenty of questions, and the growth temperature has an impact on that. The first one is what is the relation between the type of growth rate and the morphology of the polycrystalline graphene and the electric performance, like the sheet resistance, for instance, for different type of graphene morphology. So to investigate that, what you need to do is really to investigate complex morphologies which include this grain boundary. You need to elaborate models that can be done using molecular dynamics. So here you see a set of sample with increasing average grain size. And then also you have to take into account the fact that there could be some out-of-plane deformation. And then this multi-scale transport is to elaborate this type banding. So this is an example on single defect, where you do DFT, and then you compute the band structure. Then you try to find the minimal type banding model that can be enough accurate to reproduce a band structure. So with that, we can simulate the transport, and this is a result of our simulation for different polycrystalline graphene with different grain size, increasing grain size from bottom to top. And basically, we get a prediction about the case where the polycrystalline graphene is clean and typical for 1 micron, you get a mobility which is 300,000 centimeters square per volt per second, which is close to experiment. What is interesting also to plot the sheet resistance as a function of grain size, and you see that there is a reduction of the sheet resistance when you have a larger and larger grain size, which is kind of natural, but the chemical contamination of the grain boundary can increase the sheet resistance quite substantially. So this scaling law is something that has been measured by some Chinese group a couple of years ago. So it reproduced quite well the trend that we extract from the simulation. And just to point out that what is interesting, for instance, in flexible device is a sheet resistance which will have typically 100 ohms or 10 ohms. And so we don't really need to go to single grain to achieve this performance. So if we want to go very quantitative, there is an interesting measure, which is a grain boundary resistivity that you can measure when you have this kind of coalescent grains. So you measure the resistance across, or resistance inside, then you can extract this grain boundary resistivity. And when we do the comparison with the simulation, what we find is typically we have 1 or 2 order of magnitude difference. So our simulation leads to a much smaller grain boundary resistivity. But it turns out that these grain boundary are much more chemically reactive. So this has been found by imaging the oxidation of copper underneath the grain boundary, because any oxygen tends to attach more preferentially on the defects. And also this is a picture of hydrogen defect, which are mainly stitched on the grain boundary side. This is a picture given by my friend from Madrid. So we can simulate this type of effect of functionalization, and as I said, and this is typically the simulation result, we can match with the best experimental data, which are obtained when all is done in vacuum, and so this is the most closer comparison with our simulation. So now let me come to this amorphous. In 2017, Samsung and co-workers SKKU report the fabrication of a kind of amorphous graphene, and just a few years ago in Singapore at NUS, there was the first wafer scale fabrication of this really amorphous sp2 membrane. And as you see, the hexagonal rings now are completely disconnected from the presence of, from the other parts, which are really non-hexagonal rings. So the system present no short or medium range order. And what has been measured is, as I said, the resistivity is very large. The system is an insulator. One important characteristic for the system is the fact that it becomes a very interesting material for coating, because it allows to deposit a dielectric in homogeneous fashion. So we are interested in this material. We have tried to investigate the level of disorder. So indeed, you can, depending on the temperature, and these are result of the molecular dynamics, you can have different structure. And they can be also functionalized. So we have defined, you can find in this paper, the level of disorder can be quantified by this triatic order parameter. It's very interesting, and it becomes, when the smaller it becomes, the farther we are from the pristine graphene. And then you can also connect the number of non-hexagonal rings that are created and increase when you depart from the clean case. So we can follow the properties. This is an example on the density of state, or the mean free path, the conductivity as a function of the degree of disorder. We can also investigate the property which are thermal. So this is, for instance, this the thermal conductivity as a function of the ratio of hydrogenation in a system which is completely amorphous. But to finish with, I want to spend a couple of minutes on this very more recent result. For a long time, industries have been interested in finding very low dielectric materials in the context of interconnect, because they want to really reduce the problem of gate and interconnect signal delays, which is related to the resistance and the capacitance effect. So to get this, you need to find a very low dielectric constant, and which are in materials which are in addition a good diffusion barrier against migration of copper, and can be thermally and mechanically stable. And all the organic polymeric materials which have the good dielectric constants are, however, not stable enough for high treatment. So in 2020, the group of Yeon-Suk Shin and Yeonjin Shin from UNIST in Singapore report the first large-scale synthesis of this ultra-low dielectric constant amorphous boron nitride, which presents dielectric constant B even below 2, which is something that was never achieved, and the system presents a very high mechanical stability, strong adhesion, and the density, which is actually quite appropriate for the interconnect technology. So what we did is to investigate this type of materials using molecular dynamics and our models of machine learning based potential, and we found the possibility. I mean, the parameter, how to tune the parameter to get 60% of SP2, and we could also compare one-to-one a different type of disorder phases. This 60% of SP2 is in excellent agreement with the experimental data, and so we could also investigate a bit the origin of the ultra-low dielectric constant, as well as the thermal property of this amorphous thing. So a lot of things are still ongoing, but they show that this type of methods are bringing a capability of predictive modeling, which is needed for understanding and for optimizing materials for high-tech application. So finally, I want just to mention this paper where you have a broader vision about the scanning property. This material is not just electrical property or thermal property, but also mechanical property. So a kind of guideline to really adjust the materials and to find the condition for the growth which are optimal for the given application. So my time is over. I thank you again, the committee, for inviting me, and now I hope I can have some question live, and I would be very happy to answer them. Thank you very much.